In lecture 14 of particles, of symmetries, particles and fields, we're going to develop the Cartan-Weyl basis for Billy algebra. Properties of the killing form that we've already proved will come in very handy for this, particularly the invariance property. We'll be using that several times. And by the end of this lecture, I hope to reach a normalized basis for the Cartan-Weyl subalgebra and go on to define root strings, which is the beginning of the setting up of this geometrical picture of groups, or at least representations of groups. Okay, so we have this important equation 6.2, which tells us what an element, the Lie bracket of an element of the Cartan subalgebra, basis element acting on one of the roots in the root set of the Lie algebra gives us. All right, so a general element of the Cartan subalgebra, of course, is just some linear combination of these basis elements. So we'll just write this general element as H, and this is defined to be EIHI with a sum over the I. So these EIs are just complex numbers. So if we now consider the Lie bracket between H and E alpha, we just substitute in for H, and this is equal to EIHI, E alpha. Okay, which is equal to some number which I'm going to call alpha H times E alpha, where if you just look at the definitions, you'll see that alpha, we've defined this alpha H to be E alpha times alpha I. So we get this combination of the components of the roots. So each root defines a linear map to complex numbers from the Lie algebra. So it takes us from the Lie algebra of H to some complex number because of the because it takes us to this alpha. So in other words, the roots are elements of the dual of the Cartan subalgebra. So I'm going to call that LH star, the dual of the Cartan subalgebra. So it turns out that the roots are non-degenerate. So our root set consists of dimension G minus the dimension of the Cartan subalgebra, which is R, remember, elements of LH star. Now we're in a position to define the Cartan-Weyl basis for the Lie algebra. So we define our basis B to be a set of basis vectors for the Cartan subalgebra first. So these are labeled by I from 1 to R, as we said before. And then we add these to these E alphas, where alpha is in the root set. So these are our Cartan-Weyl basis vectors. So recall now that we're considering a simple Lie algebra. So the killing form is non-degenerate. So now we're in a position to be able to prove some useful results about the killing form in this particular basis. Curly kappa in the Cartan-Weyl basis. So we're going to have 4 results, and we will do the proofs. Let me just, we're going to need this equation here. So let me just call this equation star during this lecture. So firstly, the first result is that the killing form of any element of the Cartan subalgebra and E alpha is 0. And this is for all H in the Cartan subalgebra and all roots in the root set. So the proof of this is for all H prime in the Cartan subalgebra, we can consider that alpha of H prime times the killing form of H and E alpha. Well, we know that this killing form is bilinear, so it's proportional to H. And because of equation star, we know that alpha of H prime on H is just equal to the following. Sorry, alpha of H prime acting on E of alpha gives us back, is equivalent to the commutator of H prime and E alpha. So this is star that tells us this. So now we use the invariance property. Sorry, I think the invariance property uses this one. But of course, the elements of the Cartan subalgebra have a 0 Lie bracket, and so this killing form being proportional to each of these elements is 0. So we get our result. Secondly, we have that the killing form of E alpha and E beta is 0 for all alpha and beta in the root set, and alpha not equal to minus beta. So to prove this, again, for all h prime in the Cartan subalgebra, if we consider alpha h prime plus beta h prime acting on killing form of E alpha E beta, well, again, we can use our starred equation for each of these terms, and we get the killing form of h prime Lie brackets with E alpha, comma E beta, and the second term we get E beta. And then, so invariance tells us that the sum of these two things is 0, invariance. Okay, so the left-hand side, is proportional to this alpha of h prime plus beta of h prime. So this thing is just E prime I alpha I plus beta I. So if alpha I plus beta I are all non-zero, or some of them are non-zero, then we must have that the thing that multiplies it is equal to 0. Okay, the last two proofs are by contradiction. They're very similar arguments actually to each other. So for all elements of the Cartan subalgebra, there exists another element of the Cartan subalgebra such that the killing form is not 0. Of the killing form of the 2 is not 0. So the proof of this is suppose the opposite, and then we'll prove that that leads to a contradiction. So suppose for h in the Cartan subalgebra, there is, so the killing form between that element and all other elements is 0 for all h prime in the Cartan subalgebra. So now we use property 1. So 1 implies, or actually 1 states that the killing form of h and E alpha is 0 for all roots in the root set. But then if we combine this with the fact that the killing form is going to be 0 for all elements of the Cartan subalgebra as well, then the two of these things together imply that k for h and any x in the Lie algebra is 0. And this can only, this by definition means that the killing form is degenerate, but we're considering the non-degenerate case. So that's a contradiction. So we've supposed the opposite and proved that it leads to a contradiction. So fourthly, if we have an element of the root set, then we're going to show that minus that element is also in the root set, and that the killing form of E alpha and E minus alpha is not 0. So the proof here actually comes from the first two results. So 1 and 2 together imply that unless minus alpha is a root, they basically imply that the final result. So okay, well, let me show you. So 1 and 2 together. These imply that unless minus alpha is a root, sorry, excuse me. And the killing form of E alpha and E minus alpha is non-zero, then the killing form of E alpha and x is equal to 0 for, again, for all x in the Lie algebra, which would imply that the killing form is degenerate. And again, we've reached the same contradiction because we're looking at cases where the killing form is non-degenerate, simple groups. Okay. So 3 implies that the killing form gives a non-degenerate inner product just on the Cartan subalgebra. So let's take 2 elements of the Cartan subalgebra. We're going to expand them. So H again is EI, HI, and H prime is E prime I, HI. Then the killing form of H and H prime is kappa IJ, EI, E prime J. And so this kappa IJ, if we make a matrix out of it, this is invertible because it's a non-degenerate. So it's invertible and it's R by R. So we're going to call the inverse, again, just like kappa AB, we'll put the inverse with indices upstairs. So from the inverse, kappa to the -1, which has indices upstairs, we get a non-degenerate product inner product on the span of the roots in this dual to the Cartan subalgebra, this dual space. So in other words, alpha in a product with beta is alpha I, beta j, kappa to the -1, ij. So we'll use this following on quite a lot. All right, let's fully evaluate the Lie algebra now in the Cartan-Weyl basis. So we've got some of the Lie brackets so far. we certainly have that HI and HJ have a 0 Lie bracket for I and j going up to R. And we have that HI and E alpha is alpha I, E alpha for all alpha in the root set. That's what I'm going to call 6.3. But we're missing the Lie bracket between E alpha and E beta, between two of the different operators corresponding to roots. So we're going to go about finding this now, and we can use 6.3 to do it. And so we start off, what we need to do really is find what the commutator, the Lie bracket of HI with E alpha, E beta is. Okay, that's going to tell us what this bracket is. So we use the Jacobi identity first. So this is minus E alpha, E beta, and HI, minus E beta with HI and E alpha. Okay, so we know from 6.3 what these brackets within are, and we just get alpha I plus beta I, cancelling the minus signs, E alpha and E beta. So, right, now, if alpha plus beta is in the root set, then this comes under the auspices of 6.3. And so 6.3 implies that this is 6.3. So it's proportional to E alpha plus beta if alpha plus beta is in the root set. That's what 6.3 implies. And it also implies that it has to be 0 otherwise, as long as alpha plus beta is not 0. Okay, so we have this, so we know what the bracket's going to be, except for this one case where alpha plus beta equal to 0. And that's the last case to work out. So for this case, we need to consider the Lie bracket of E alpha with E minus alpha. So here let's consider the killing form of E alpha, E minus alpha with H. Now we use the invariance property to tell us that this is equal to kappa of E minus alpha and H with E alpha by invariance property of the killing form. And then 6.2 tells us, or actually 6.3, no, 6.2 tells us that this is equal to alpha of h, kappa of E alpha, E minus alpha. And remember that this thing is non-zero according to property 4, which we've just proved. Okay, now if we define a kind of scaled bracket, H alpha, so we define it to be E alpha, E minus alpha over killing form of E alpha and E minus alpha. This is in the Cartan subalgebra. And that's because, you know, from the line above it, implies that K of H alpha and H equals alpha H. So it's in the Cartan subalgebra. So H alpha solves an equation which is well, it solves this equation basically for all H in the Cartan subalgebra. And it does it uniquely because it's non-degenerate. Okay, so if H alpha is in the Cartan subalgebra, we can expand it, which we've shown it is, we can expand it in terms of some coefficients. So I'm going to give these coefficients a label, the label alpha, and we sum over, so that these coefficients will be different if you've got different alphas, but we just sum over the different elements of the Cartan subalgebra. And our H in this equation is just going to be rho I times HI. So this equation over here, I'm going to call 6.4. So 6.4 then becomes kappa ij. So we just substitute H alpha into it. I alpha rho j is equal to alpha I rho j. And this has got to be true for all rho j, which, so we can basically effectively cancel the rho j's off because it's equivalent for all of them. So kappa ij rho I alpha is equal to alpha j. Okay, so I can use the fact that this kappa ij has an inverse, a unique inverse. Which we wrote like this, and just multiply on the left by such an inverse. We call this 6.4b. So we just substitute this rho I alpha back into the original, or back into H alpha. So we've got kappa to the -1 ij alpha j hi. Okay, so now I can work out the commutator of H alpha with E beta. So this is kappa. So I substitute in for H alpha. Now this is kappa to the -1 ij. And we get alpha j beta I. E beta. So if you look and see what that this is equal to in a product of alpha and beta times E beta. And this is for all, remember, this is for all alpha and beta in the root set. Now, I did mention it, but we've really assumed that the roots are non-degenerate. So I'm going to also assume that the length of each of them is not 0. Now, you can relax both of these assumptions, and the proofs get much more involved, but they're not very instructive. So we're just going to stick to this for now. All right, so now we define a normalized basis for all of the roots in the root set. So we define some little e alphas, which are proportional to the big E alphas, and the constant of proportionality is square root of 2 over alpha alpha times kappa of E alpha E minus alpha. It's within the square root as well. And little h of, little h suffix alpha, so this is definition, is proportional to h alpha. And this is going to be 2 over the length squared of alpha. And so we can rewrite our Lie algebra just in terms of these normalized in this normalized basis. Okay, so once you expand H alpha out in terms of the Cartan subalgebra basis elements, you just get some coefficients times commutators of the Cartan subalgebra here. So whatever the coefficients are, it ends up giving you 0. And if we consider little h alpha, Lie bracket with little e beta, this comes out to be twice alpha beta over alpha alpha E beta. So you can just check that by substituting in for H alpha and E beta, putting in the constants of normalization, and using our previous commutators between big E's and big H's. And then little e alpha, Lie bracket with little e beta. Well, this, we get something proportional to e alpha plus beta if alpha plus beta is in the root set. So we're going to call that the something n alpha comma beta. And these n's alpha comma beta is just going to be some complex number. And then we get check that the normalization is such that we get h alpha if alpha plus 0 beta is 0, and you get 0 otherwise. So if one root is not minus the other one and they're not in the root set, we get 0. And so this is where n alpha comma beta is a complex number. Okay. We call this 6.5, all of these, this Lie algebra in this normalized basis. Now, this implies an important thing. For every root, there's actually an SU2, a Lie algebra of SU2. Over the complex numbers. There's a subalgebra, and it's generated by the set just H alpha, E alpha, and E minus alpha, since you can check that 6.5 implies that H alpha and E plus or minus alpha is plus or minus 2 E plus or minus alpha, and E alpha, E minus alpha is H alpha. Now, if you look back at our SU2 Lie algebra, you'll see it's precisely this. So for every root, we get a complexified SU2 subalgebra. And okay, so because the complexified SU2 is similar to this SL2C, then it's customary to call this subalgebra SL2, but we want to give it, there's one for each alpha, so we'll label it with a suffix alpha. So this is after the fact that, you know, the Lie algebra of SL2C is the Lie algebra of SU2, as we mentioned a little while ago. So that's where this SL comes from. It's the special linear. All right, so we've just got one topic now before the end of the lecture, which I'll just introduce, and we'll carry on with it, developing it next time. And these are root strings. So given two roots in the root set, these are vectors in the root set with, well, let's say they're different ones. The alpha string passing through beta this is a definition. The alpha string passing through beta is the following set of roots. So we're going to denote it with an S and an alpha comma beta suffix. So this is just beta plus rho alpha, where rho is just some integer. So we add rho times alpha onto beta, basically. So for a given root string, there's a corresponding vector space. And this we'll call V alpha beta. So this is the span over the complex numbers of the various E of E beta plus rho alpha, where, oh, sorry, I missed out on a very important thing. So we take all integers rho, but we only take the results where it's in the root set. Okay, so we add rho times alpha to beta, and if it's in the root set, it's in this alpha string passing through beta, otherwise it's not. So now we have the span of each of these elements of the root string. Okay, so next time we're going to go on and use these root strings further, and we'll start to build up the groups, the Lie algebras at least.